Ever wonder how a chunk of pure, boring silicon ends up powering your phone, your computer, and even solar panels? Hello and welcome to the Science Reference Desk. I'm your host Joseph, and today we are exploring doping in silicon wafers. Doping is the critical process that transforms ultra-pure silicon crystals into functional semiconductors by introducing microscopic amounts of impurity atoms like phosphorus, N-type, or boron, P-type, into the silicon lattice. Manufacturers tailor electrical conductivity for components. In semiconductors, N-type and P-type refer to the kind of electrical charge carriers that dominate in the doped material. Here's a simple breakdown. N-type semiconductor are negative type. What does that mean? The majority charge carriers are electrons, which carry a negative charge. How is N-type made? Pure silicon is doped, intentionally contaminated, with an element that has more valence electrons than silicon. This is typically phosphorus or arsenic, which have 5 valence electrons. Why does it work? Silicon has 4 valence electrons and forms 4 bonds. Phosphorus brings an extra electron, which becomes free to move, creating greater conductivity. What are the results? Extra free electrons increase the material's ability to conduct electricity. Here is a memory trick. N-type is negative electrons. Now for P-type semiconductor, which are positive type. What does that mean? The majority charge carriers are holes, which are positive charge vacancies where an electron is missing. How is P-type made? Silicon is doped with an element that has fewer valence electrons like boron or gallium, which have only 3 valence electrons. Why does it work? The missing electron in a bond creates a hole, and as electrons from neighboring atoms move to fill it, the hole appears to move. This movement of holes carries current. What are the results? The semiconductor conducts electricity via positive charge carrier holes. Why are both important? When you place N-type and P-type materials together, you get a PN junction, which is the foundation of diodes, transistors, solar cells, and all modern electronics. Even modest doping increases conductivity by millions to billions over intrinsic silicon. Precise doping depths and profiles are essential for forming PN junctions in devices. This precise tuning enables the billions of devices we rely on every day by creating controlled electron-rich or hole-rich regions. The process involves methods like ion implantation and diffusion, followed by thermal activation and metrology to achieve the desired carrier concentration and sheet resistance. Want more deep dives into the science powering our world? Hit subscribe and join me for more awesome science learning videos.